Well, tonight I am very pleased to introduce our speaker this evening. It's somebody that was introduced to me by a friend of mine in another organization as somebody that works at the David Clark Company in Worcester. Some of you may know David Clark Company. The name may be familiar. They have a long history with pressure suits and working with NASA and the military. But tonight I'm very pleased to have our speaker, Nick Deane, and he is a project engineer with the Aerospace Life Support Systems at the David Clark Company in Worcester. And he's also responsible for bringing us the incredible deflating man on the table, which he will talk about. So that actually has quite a bit of interesting history along with it. Some of you talked to him a little bit before the meeting. So I don't want to take any more time from you, Nick, but if you want to come up, we'd love to hear from you, and thank you for coming.
Thank you, guys. Thank you so much, Steve, for that warm welcome. All righty, let's hop into it, because I'm sure you're all going to have a lot of questions. So yeah, you can go to the next slide.
Oh, yeah, you got the message.
Oh, that's right, you gave me the mouse. Sorry.
No, you're good. I can do it that way if you want.
So my name's Nick Deane. I'm a project engineer, like Steve said. Just a little bit about me. I graduated from UMass Lowell with both my bachelor's and my master's degree in mechanical engineering. Go Riverhawks. And my master's thesis research was on basically the impact of military equipment, specifically EOD suits on the human body. So this is a picture of me wearing the EOD-8. I don't know if any of you have seen the movie The Hurt Locker with Jeremy Renner, but that's basically the exact suit that they wore in Iraq and Afghanistan and other countries for disarming improvised explosive devices. And if you couldn't tell, it's a big clunky suit. It's very uncomfortable, especially if you're in an area that's like 100+ degrees. So we were looking at what we call human factors. So the wearability of the suit. I was specifically looking at hot spots between the suit and the body, like at the shoulders and whatnot, and basically collecting that data for the U.S. Army. And what's funny is my focus in mechanical engineering was originally robotics. I was even doing robotics internships. And because of my master's thesis, I finished writing my thesis and defended it during COVID. And I was, frantically looking for a job because this is when, the economy crashed during COVID. And I didn't want to have to commute to Boston because I'm from Central Mass. Originally, and I saw there was an opening at a company called David Clark for project engineer. I had no idea what they did. I did not know anything about their background. I had no idea that spacesuits were made in Worcester. And when I got to the interview, I was blown away. I was like, oh my gosh, I really hope I get this job. I really want to work on spacesuits. And because of my experience with these bomb disposal suits, that was what ended up getting my foot in the door. So, and I've been working at the company since September 2020. So David Clark is basically two companies. So there's David Clark in Worcester, Mass. And then our sister company, which is part of like the David Clark Holdings, is Airlock in Milford, Connecticut. I was actually there yesterday to talk some project proposals, but they do all these fancy metal connectors for connecting the gloves and the helmet to the suit, among other things. And they're basically the only company in the world that does those types of connectors, because the Russian spacesuits, the SpaceX spacesuits, as far as I know, with the Chinese spacesuits as well, everything's kind of like integrated. They don't really detach from the suit itself. So our suits and the suits built by ILC Dover are some of the few that have like disconnectable helmets and gloves and whatnot, using Airlock's technology, which is just made by some of the most experienced machinists. And then we have this little spot marked in Houston, Texas. We don't really have like a location down there, but we have our two systems engineers who work remotely. But they basically have their own office at Johnson Space Center. And lately they've been working more with Axiom, which is a company we're subcontracting through on the new lunar suit and EMU suit that they're building. So just brief history on Mr. Clark. So David Clark was basically a born inventor. He worked in his father's garment factory growing up, and he did not want to go to college. He very much just wanted to get right into it, get to inventing, get to owning his own business. So his father basically had an agreement with him that if he did, 1 year of college, he would help his son set up his own, garment business. So when David Clark, the company, was founded in 1935, what they first made was men's undergarments and women's undergarments. So things like
The projector.
tank tops or bras and brasiers. That was originally what the factory made at the old location. But then something called World War II happened, and Mr. Clark, being this inventor, wanted to solve this problem known as pilot blackout. So, we went from the biplanes, these old rickety biplanes of World War I, to planes like the P-51 Mustang during World War II, which could hit speeds of 700 miles per hour, which means that if you were pulling a turn, the G-forces from that turn could be so intense that the blood would leave your head and you would be knocked unconscious until you came out of that turn, regained conscious. So this prevented pilots from doing these high G maneuvers and affected their combat effectiveness when dogfighting the Germans or the Japanese. So Mr. Clark invented what we now know as the anti-G suit, which is still used to this day and is not much different from his original prototype. So the prototype anti-G suit was made out of football bladders that he had stitched together, and it's 4 chambers or 4 pressurized segments. So the calves, the thighs, and then the belly section, and then obviously it's mirrored on the other side. And he also had airlock, which at the time was called, I think it was called the Milford Machining Company, and they basically worked together to design this. And Mr. Clark famously sold the technology and the idea to the U.S. government for $1, because for him it wasn't about the money; it was about the war effort. And that we actually have that dollar framed in our little museum at the company. And this obviously the anti-G suit went through some further iterations, and it was huge. So I have here fighter pilots in the 8th Air Force reported a 50% increase in combat kills wearing Clark's G3 suit. So we don't make current anti-G suit now. So basically, when the patent expired, other companies like Gentex makes them. But we are actually trying to stick our hat in the ring again with a new updated one. That's pretty cool. So World War II. World War II. Ladybug. So World War II is how the company really transitioned from doing underwear to spacesuits or pressure suits, starting with that anti-G suit. But then from there, Mr. Clark's company was then working on suits for NASA, which at the time was part of the Air Force, for these prototype jets that they were working on. So this is the Bell X-1, the X-15, which a lot of folks are familiar with. These early suits were really important for that initial push for human space flight. One of the other companies that was working on spacesuits at the time was B.F. Goodrich, actually. And so David Clark didn't start making spacesuits for NASA until the Gemini program. So all those Mercury era suits were mostly made by B.F. Goodrich. So going from the suits that we made for those prototype aircraft, then when the Gemini program came around, the David Clark company was making some of these early IVA EVA models. So IVA means intravehicular asset, meaning you wear it inside the vehicle. EVA is extravehicular asset, meaning you wear it outside the vehicle. But some of these early suits were hybrid IVA, EVA suits, including, if you want to go to the next slide, the suit that Ed White wore when he did the first American spacewalk on June 3rd, 1965, wearing our G4C suit. So he was wearing that suit inside his little capsule, and he wore it, the same suit, when he was outside as well. So it was like a hybrid IVA, EVA suit. So from Gemini, the David Clark company. So common misconception, we did not make the full Apollo suits. So Airlock made all the disconnects for the air inlets, for the gloves. So our sister company Airlock made all the disconnects. The David Clark company did make what we now know as the Snoopy cap, so the con carrier that they wore in the suit. So that was really our but we did do some prototype suits, but basically we lost out on the bid to a company called ILC Dover back during the Apollo program. So that's that puffy white A7L, A7LB. Those suits were made by ILC Dover, not us. And then ILC Dover also makes that puffy white EMU suit that they wear on the space station. So I just wanted to clarify that. But while ILC Dover was working on those suits, we were working on suits for the shuttle program. So these were IVA suits, intravehicular suits. So for those early prototype shuttle missions, we had developed the S1030A escape suits, as well as the S1032 launch entry suits, and those ultimately became the platform, or even related to the suits that we were using for the U-2 spy plane and the SR-71. But then they also evolved to the ACES suits. This is probably the suit that most people are familiar with for David Clark, which is that iconic orange pumpkin suit from the shuttle program. And that's our suit. Those were made in Worcester, Mass. I include, so for this presentation, I include pictures of the shuttle program because I was alive for the tail end of it. I think it ended around 2011 was probably when the last launch was. So when I go to present at some of these schools, I forget that a lot of the kids don't even know what the shuttle looks like, you know? So I had to include a picture for the younger generations. So this is the suit that I have right here. This is our S1034 PPA. This is probably our most produced suit. We've been making this suit for the Air Force for a long time. The early versions of this suit can be seen, I mentioned it to someone earlier, the movie Bridge of Spies, the Steven Spielberg movie about Gary Powers was forced to eject over the Soviet Union. He was wearing one of our suits, but it was actually pretty different from this suit, which I'll maybe get into a little bit later. But this suit was worn, this suit's worn in both the U-2 spy plane, which is still in flight today, and it was also worn in the SR-71, which was retired somewhere around 1995. So this is a picture of the U-2 spy plane. For those who aren't familiar, it's a high altitude jet. It's pretty incredible. It's basically like a giant glider with a rocket motor, you know, with a jet strapped to the back of it, and it's capable of flying over 70,000 feet. So this thing pretty much flies close to what we would consider to be, you know, the edge of space, or well over the Kármán line. I believe it flies up to 90,000 feet max. And those missions that those pilots go on can be anywhere from 8 to 12 hours in one go. And basically they just fly these big arcs over whatever they want to monitor, because, and the reason why they still use the U-2 spy plane is because for satellites, you have to wait till they come back around. So if you have a manned plane that can constantly fly over, and you can keep flying over, you can get more data in between those satellite passes. And that's what these pods on the U-2 are for. So those can actually be changed out, and they can put different sensors or cameras on them, and those will be used by the CIA and military intelligence. So we'll see if this video works. We might just wait a second or two and see if it plays. but it's something that I was lucky enough to experience. So what you can see in this, if the video doesn't work, what you can see in this this screenshot here is the landing gear of the U-2. So there are no landing gear on the wings. It's just these two landing gears on the center of the fuselage. And it's basically like landing the plane on two pogo sticks. And because of that, and because the U-2 spy plane has that big nose on the front of it, and because the pilots has limited visibility because the spacesuit that they're wearing, they have to have a chase car when they take off and when they land. So I was fortunate enough to visit Beale Air Force Base in California, where I met with the U-2 pilots and the Air Force crew that maintains the suits and the planes. And I got to ride in the chase car, which is driven by another pilot. And basically, they're doing 120 miles per hour right behind the plane. Yeah, the video might not work. It's just a YouTube embedded link, so I'm not sure if it's going to work or not. It's okay if it doesn't. But yeah, basically, that's how close the plane is to you when it's landing in front of you while you're doing 120 miles per hour in a Dodge Charger behind it. And the pilot who's driving, so while he's driving behind the U-2, while it's landing right in front of him, he's radioing the distance of how close those pogo stick landing gear are. So he's going 10, 6, 10, 8, 6, like as he's coming down. And he's just doing it from just guessing basically, because he has no way of measuring it. He's just from intuition. And the other pilot just has to trust him, right? And then what happens is once the plane lands, it just tips over to one side. So there's these titanium skid plates on the wings. It just tips over, and then they put it on like these training wheels that go under the wings. So when they're taking off, they have the training wheels on, and when the plane takes off, the training wheels fall away from the wings. And these are just all design constraints from when they were designing this, high altitude aircraft. So this is considered one of the most difficult airframes to fly in the military to this day. And then this is another suit that I think a lot of people are familiar with. So sadly, Felix Baumgartner passed away last year in a I think it was a paragliding accident in Italy or something like that. So he definitely died how he lived, which was on the edge. The man was a daredevil and had performed some really, truly amazing feats. And this is definitely one of them. I remember watching the live stream of this when I was in high school. This was in 2012. But yeah, this Red Bull Strato suit was made in Worcester. Joe Kittinger was actually involved with the project. So Joe Kittinger held the original jump record, which was at about 90,000 feet, I believe. And then Felix Baumgartner broke that record by jumping from over 120,000 feet. So yeah, this was amazing. And I don't have a direct link to it, but if you were to Google it, there is a white paper that was written by NASA with all the data that they collected on this. And that was the only reason why our company agreed to do this Red Bull stunt, was because we basically said, we're not just going to do this just to break the record. We want to make sure that there's going to be good scientific data to glean from this, because that's part of our reputation. So that was the reason why we agreed to help Felix do this jump and to make this suit for him. And we have that suit on display in Worcester. All right, so now we're gonna get into a little science. I promise I'm not gonna make you do any math. And basically talk about how these suits keep people safe and the dangers that we're looking at. So first, just for those who forget, the majority of our atmosphere here on Earth is 78% nitrogen roughly and 21.8% oxygen. And then the rest is just other gases, CO2, argon, etc. But when we're breathing air, this is what we're breathing in. And our atmospheric pressure is, so the pressure here on Earth is around 14.7 psi. So we breathe the air in, the mostly oxygen and nitrogen mix, and then we exhale out carbon dioxide. So remember this, as I'm sure you probably already know. So combined with the air allowing you to breathe, the air on Earth is also squeezing you from all around, which is also keeping you safe. So the air that we breathe also serves this dual purpose of pressurizing us here on Earth. So now we'll get into the dangers of outer space when you don't have that air around you. So you would be, if you were in outer space without a spacesuit, you would become unconscious within 15 seconds due to lack of oxygen. Your blood and bodily fluids would boil and then freeze from the lack of air pressure. Your tissues and organs can then expand from the boiling fluids. And if there's any nitrogen in your blood, the nitrogen will actually bubble out from your tissues and can potentially be carried by your bloodstream to your brain. This is what scuba divers refer to as the bends. And it's basically like nitrogen poisoning of the brain. So we don't like nitrogen. You would also face extreme temps, ranging anywhere from minus 148 degrees to 248 degrees. So yeah, if the sun's directly on you, there's no atmosphere to interrupt that. You would also be exposed to radiation. There's just a radiation from the sun itself. There's cosmic rays and solar winds, which are more dangerous. And then you could also be hit by small, high-speed particles such as micrometeoroids or even orbiting debris from all the junk we have in low Earth orbit. So to protect you, a spacesuit has to serve a variety of purposes. So it has to maintain a pressurized atmosphere similar to the one here on Earth. And it has to supply oxygen while also washing out all that carbon dioxide. It also needs to protect you from that flying space debris, just the small stuff, and try to protect you from as much of the radiation as it can. It also needs to allow you to see clearly. So the astronauts who work on the space station, they have to be able to see what they're doing. Or if the astronauts in the space shuttle have an emergency, they have to be able to see what they're doing in the cockpit. You have to be able to move inside the suit, so it can't just be rigid like a balloon. It needs to provide cooling. It gets hot inside spacesuits because you're wearing all these layers, so it needs to provide cooling to prevent heat exhaustion. And it needs to allow you to communicate. So you got to be able to talk with your fellow astronauts, talk with ground control in Houston, etc. So now when we get into, well, how do we design a spacesuit? So what I do at my job, there's kind of all these terms that float around because there isn't always one way to do things with spacesuits. So I have some of these terms floating around, and I promise I will touch on all of them. And we even touched on some of them already, like IVA and EVA. Next, the design of a spacesuit primarily is going to depend on what your mission is, right? Are you doing just a suborbital flight test where the person stays in the capsule the entire time? Is it just a short trip to the ISS? Or are you going to try to explore the moon or another planet like Mars? So you have to watch out for, over designing a suit because that can add unnecessary weight. And when it comes to going to space, your weight bank is everything. You want to reduce weight as much as possible because for those of you who watched the Artemis 2 launch, you have that giant rocket just to send 4 people around the moon once. So think of the cost of all that fuel and the cost of building a rocket like that. And that's just for 4 people. So as I was explaining earlier, you have basically 2 different types of suits. You have the intravehicular activity suit and the extravehicular activity suit. The intravehicular is inside the ship, and you basically are wearing the suit only in the case of an emergency. So for this yellow U2 suit, for the Artemis, the orange Ox suits for the Orion capsule, That blue suit was the one that we made for Boeing Starliner. Those suits are all just worn in the case of an emergency, right? But otherwise, the capsule that they're in is providing all the air and pressure that they need to breathe and survive. The suit's just there in case they lose that cabin pressure or that cockpit pressure. The extravehicular suit, however, that suit is your only lifeline. If you're out on the moon, if you're out on the space station, that suit is basically your own personal rocket ship or your own personal capsule, your own personal spaceship. So the other thing that we have to look at, as much as, as engineers, we'd like to design everything, however we want to our own idea of what perfection is. Unfortunately, you have something called requirements. And those requirements come from the customer. The customer could be a private space company, like Boeing or Axiom, or it could be NASA. So if they're the ones building the capsule, they're basically going to be the ones to dictate to you, well, the seat is going to be this big. So you got to make sure that all the elements of the suit, fit within the envelope of that seat. We're also going to have this type of harness. So you got to make sure, your air inlet or your air outlet connectors don't interfere with the harness. Your comms, they're going to plug in with this connector. So you have to use this connector. Anti-flail restraints, you have to, we've had to integrate things like that. So anti-flail is basically ways of locking your legs or your arms in, because sometimes if there's an emergency and you have a lot of vibrations or a lot of G-forces, you don't want your limbs flailing around because that's how bones get broken. There are also fighter plane ejection seats that have flail arrest systems as well. And then also, is it going to be a touch screen or is it just going to be buttons? Because then that will determine if you need to use certain fabrics or coating on the gloves. That will then allow you to touch the touch screen. And then there's also, capacitive versus resistive touch screens and stuff like that. So these are the types of requirements that are flowed down to us by someone like NASA. And then we also help write the requirements as well, just from our own experience. But these are the things that basically constrain the design of the suit. So there's also the question of what's the suit going to be pressurized to, right? So basically, you could have what I would refer to as a low pressure or a high pressure suit. So something like this Air Force suit or the Boeing suit that I show in the picture, which is just designed for going to the ISS. These are what I would consider to be low pressure suits. So typically pressurized between 3.5 and 4.3 PSI differential. I'll explain what that means in a sec. So what's the pros of having a low pressure suit? Well, when you pressurize the suit, right, you're putting stress on it by filling it with air or with oxygen. If you have low pressure in the suit, you're not going to have as much stress being constrained. So you're going to lower that hoop stress, and it's also going to allow you to have more mobility in the suit. So lower pressure means you can maybe move your arms a little more easily or your legs if you had to. So you have less movement restriction. But the cons is that with these low pressure suits, you have a longer, what we call pre-breathe. So pre-breathe, I mentioned the nitrogen earlier. So the Air Force pilots, when they get in these suits before they go on a flight, so they've been breathing the air here on Earth the entire time before the mission, right? So they have nitrogen in their blood and in their tissues. So what they do is they purge that nitrogen by putting on these suits, and then just while on the ground, they sit in these big recliners, and there's an Air Force tech running 100% oxygen into the suit, and they basically just breathe 100% oxygen to just purge all that nitrogen out. Then they go in the plane and run their mission. They do the same thing with the EMU suits when they go to fix something on the ISS. So EMUs take so long because they have to do about 4 hours of pre-breathing prior to going out of the airlock. And it's like it happens in several stages, and they'll even do workouts while wearing a mask, breathing in 100% oxygen before then getting in the suit and breathing 100% oxygen. And all that is just to purge all that nitrogen out so they don't risk getting the bends. Sorry, go back. I'm bad.
Oh, you're good.
What
have I done?
You're good.
There we go.
Yep, perfect. So then we have the what I would call high pressure suits. There are not a lot of instances of high pressure suits. In fact, the Orion suit is one of the few I know off the top of my head. I think the other one might be the SpaceX suits. But the Orion suits, they are designed to, in an emergency, first they shoot up to 8 psi. And the reason for that is because the astronauts don't have time to do a pre-breathe in an emergency. So the suit just immediately pressurized to 8 psi, and then they just sit at 8 psi to basically breathe the pure oxygen for a little bit at the higher pressure to help wash that nitrogen out. And then they actually will bring the suit manually down to 4.3 so they have the ability to move, so they can do what they need to during that emergency. Now, the cons of having that higher pressure is now you're putting much more stress on the suit, so the suit needs to be stronger. You need reinforced stitching and maybe some more layers of materials. And then because of that added bulk and that added pressure, you're also going to have movement restriction as well. So now I'm going to explain what I meant by PSI differential or something like PSI gauge. So this basically helps explain what pressure these suits operate at. So the example that I always use is a car tire. So a car tire on average is inflated to about 32 psi. I think newer cars are around 36 psi. That when you fill your car tire and you're reading the gauge, that is what we literally call the gauge pressure. It's not the absolute pressure. So the absolute pressure is the gauge pressure, that 32, 36 psi that you're reading on the gauge when you fill your tire, plus the pressure of the atmosphere pushing on the tire all around it. So when you inflate a tire to 32 psi, it's technically 32 psi plus the 14.7 psi of Earth's atmosphere. And that is what we call the absolute pressure. And that is the principle that the relief valves on these suits operate at. That's what prevents the suit from overinflating when it fills up so fast, or it just keeps the pressure regulated. So it's basically this advanced relief valve that instead of controlling the gauge pressure, which if you have an air compressor, the relief valve on that is calibrated to gauge pressure. These are calibrated to your absolute pressure. So they're designed that way to work if you're in a vacuum or a low atmosphere environment. So now we have closed loop versus open loop. And again, this just all kind of depends on what your mission is. So for the Boeing suit, which was designed for just going to the ISS and back, this is what we call an open loop suit. So you have fresh air flowing into an umbilical, into the suit, and then the exhaust, the CO2 that you're exhaling, just gets washed and flowed out just through an open valve that just vents into the cabin of the capsule. Now, the Orion suit, these are actually the early prototypes of the Orion suit that were just modified ACES suits from the shuttle program. These are what we call closed loop suits. So you have an umbilical that's not only bringing fresh air into the suit, but then you also have a separate umbilical on the other side that's taking that waste product, that CO2 out. And again, this is typically just dependent on the length of the mission or how far you're going to be from Earth and the types of emergencies that you could see. So, and that's what we're going to get into with this slide is, what's the plan in case of emergency and how is the suit supposed to act? So, depending on the configuration of the vehicle, how will the astronauts be protected from different, what we call CONOPS, contingency operations. So we have what's called feed the leak. So what that is the capsule's ECLS or its environmental control system will try to, maintain cabin pressure, and if it can't, then it'll start pressurizing the suit, flowing pure oxygen to the astronauts in the suits. And it can even control the O2 concentration if needed as well. You also have what we call get the smoke out. So if there's a fire in the capsule, I know the Boeing suits are designed to just rapidly flow air to just make sure that no smoke is getting inside the suits through that outlet. And then there's also, emergencies that you could have on the ground. So let's say there's a fire while the rocket's on the pad. So if they have a fire on the pad or an emergency on the pad, they have like those that gondola zip line that they get into to escape the capsule, which then takes them down to like an APC, some kind of armored vehicle that then drives them away to safety. But in the case of a fire for the Orion suit, they're instructed to just keep their helmet, keep their suit on. And they actually have, you might have been able to see them in the news footage, and I might have a picture here. They had these bottles strapped to the sides of their legs. Those are what we call EOS bottles, emergency oxygen system. So that's in the case there's an emergency, so they don't have to like take their helmet off and their gloves off. They can keep the suit on, and they can just rapidly flip a switch basically on both sides, and that just releases fresh oxygen to their suit. And now they're breathing that bottled air while they're escaping the rocket while it's on the pad. For Boeing, it was different. The Boeing suit doesn't have a hard helmet; it has like a soft hood, similar to the suits that they wear on the Soyuz capsules. And basically, they unzip their hood, take it off, and they have a separate hood that they put on that then connects to a separate nitrox bottle. So nitrox is basically it's oxygen mixed with nitrogen, but at an increased level. So it'll be 30% oxygen or 40% oxygen instead of the typical 22%. They flow that in this hood that they wear, and you can see this is McLean. She's wearing an emergency oxygen mask that I think is used on the ISS. So the other thing is, how much mobility does the suit need? So for a lot of these IVA suits, they're just designed to be sitting in a recumbent position the majority of the time. So when they wore the suits in the Orion capsule during Artemis 2, they're basically just sitting there and just doing some, just some basic form, fit, and function of the suit to give us feedback and NASA as well. But if you're, since we're going back to the moon, and the mission for the moon this time is different than Apollo. So on Apollo, it was just beat the Soviets, hit some golf balls, plant the flag, come home, right? That's what Apollo was. And then they realized that they were really limited by that A7L suit. And that's why they had to do, the famous, little skip tippy toe thing that they do in those suits on the moon, because they just didn't have a lot of mobility. It was kind of secondary to what they're trying to do. All the suit had to do was just keep them alive. But now that we're going back to the moon, we want to do some geological research and some experimentation and have astronauts actually living on a moon base going forward. So they're going to need a suit that has way more mobility. So you can see an early prototype concept in this picture here, where the astronaut's able to actually kneel down and pick something up, which you would not have been able to do something like that in those old Apollo suits. And then this is, I believe, a picture of my boss wearing one of our prototype suits where he's testing out this arm here that has these, it almost looks like bellows or convolutes in the fabric with this axial restraint line, that black axial restraint line, and that basically allows him to bend his arm while pressurized. And then on the picture here, all the way on the right, this is an example of some ways we try to give like an EVA glove mobility. So the IVA gloves won't have fancy stuff like this in there. This is primarily for an EVA glove. But you can see we have this linkage system that's designed to allow you to bend your wrist while pressurized. And then there's this like knit, almost looks like cargo net or knit webbing That's actually a proprietary thing, this proprietary weave that we make called LinkNet. It was created during the Gemini program by Mr. Clark. He actually even invented the machine that makes it. It's a custom machine that we use in-house. And it basically acts as a special restraint. And the knit, that link net, it can like, you can orient it in ways where it'll stretch really well in certain directions, but not in others, which is what will allow you to bend your fingers easily or move your shoulder or something like that. And then also you have cooling, right? You're wearing all these layers, the suit can get hot. So basically the two choices that we have right now is air cooling and liquid cooling. Obviously liquid cooling is going to be a lot heavier and is pretty much unnecessary for pilots or just a suit that's going up to the ISS. So typically for suits like this suit, we just use air cooling. So literally, even if they're flying and they're wearing the suit, the cockpit's pressurized. They could open their visor if they wanted to, but they shouldn't because they wear the suit in the case of emergency. But basically, they run the suit at what we call vent pressure. So we're flowing air to the suit, but it's not being captured by that valve. It's just letting the air out while the air is flowing, and that air is just to keep the pilot cool while they're flying. And then these liquid cooling garments. So on the Apollo mission, they wore what was called the LCVG, the liquid cooling ventilation garment. That this requires, an advanced life support system. So that's why an Apollo and EMU, so those extravehicular suits, they wear that big backpack called the PLIS, the Personal Life Support System. And one of the functions of the PLIS is it's to constantly run cool water through this complex array of hoses to keep the astronaut cool. And the way that works is, how does your body cool off when you're sweating, right? When you're sweating, your sweat's evaporating. That's what's giving you that cooling effect. And this works in the same exact way. The PLIS is actually evaporating the water from the suit, and that's what allows it to stay cool as it's recirculating. And now we also have communications, right? You got to be able to talk to your fellow astronauts or to ground control. I think a lot of people are familiar with David Clark for our iconic green headsets that are worn by hobbyists and pilots of planes and helicopters of all sorts here in the US and around the world. But then we also put that same technology into these comm carriers that we've made throughout the years. You might need some. So in the case of some of these suits, so this yellow suit right here, their comms are completely integrated to the helmet. They don't wear a separate comm carrier like this guy's wearing. This is what we call our Snoopy cap because it looks like the cap that Snoopy wears. And this actually has some padding in it as well to help protect the astronaut's head since the helmet isn't a conforming helmet. So if their head were to snap back, the helmet's not going to move with their head. They're just going to smack their head into the back of that bubble that they're wearing. And then similar with the Boeing suits, we actually had to put, you can see this is Sunny Williams, who flew on the Starliner mission to the ISS with Butch Wilmore, Massachusetts native, by the way. She's wearing what we call the CHIPA, Communications Headset Protection Assembly. So this one has all this foam and padding, and it even has this hard backstop to protect the back of her head because they're wearing these soft helmets or these soft hoods. So they don't have that hard fiberglass-like composite layup to protect them. They just have this hood that's for weight reduction. So they actually need padding and protection in their headset carrier to give them that protection. So actually, can you go back a slide? Yeah. I didn't write it in, but it's worth mentioning. So some of you are asking about the helmet on this suit, how it has this space barrier that looks like it sticks right to your face. So there's basically two different types of helmets for these hard helmets. There are conformal helmets and non-conformal helmets. So in the ACES suit, this is a really good mock-up of our ACES suit built by Adam Savage from Mythbusters. You can see that the helmet isn't, connected to his head in any way. So if he were wearing the helmet and he were to turn his head, the helmet isn't going to turn with his head. Whereas with this suit, this U2 suit, if the U2 pilot turns their head, the helmet moves with their head because it's attached to their face. Now, the reason why that's the case on this suit is because this suit's what we call a dual volume suit. What that means is it's suctioned. The helmet is basically has an airtight seal around their face, so they're not allowed to have beards like I do, the pilots. And basically the breathing air that they're getting, which is on demand, meaning they only get air whenever they breathe in like that. So there's a diaphragm that's letting air in when they breathe, and that breathing air is only in this part of the suit, just where their face is, just in that portion of the helmet. So the air to pressurize them, right, that pressurizes them, that's separate. So that cooling air is what actually pressurizes them to give them that, atmospheric like pressure to keep them safe. Whereas the breathing air is completely separate. Now, in the Orion suits or the or even the ACES suits from Shuttle, it's a continuous volume suit. So it's not segmented like this suit is. So the air you're breathing is also the air that's squishing you to keep you safe as well. I just wanted to mention that. So here's some of the exciting, more recent things that we've worked on. So obviously we have the Artemis 2 crew. What a stunning success that was, and it was just absolutely amazing to watch on TV. I worked pretty heavily on the gloves on that suit, but I've also tested and worked on different aspects of that suit. So I'm incredibly proud of those astronauts in the Orion suit that we all work so diligently on. This is the what's called the AX EMU, AX for Axiom. So we're subcontracting with Axiom on the next generation lunar suit and the next generation EMU suit, or they're calling it the LEO suit, the low Earth orbit suit. But this is the initial prototype that they released to the public of the AX EMU suit, the suit that's going to actually go to the moon. And people always ask me, why is the suit black when other suits are white? And I said, because it looks cool for the media. So the color is actually, for EVA suits, color is very important. We would never send a black suit. Does anybody know why? Yes, because what does black do? Absorbs, and white does reflects. Exactly. I should have known you guys would be so smart. So yeah, this was just to look cool. Black has that slimming effect, like tuxedos. So this was pure marketing from Axiom, because obviously they want to get more investors besides NASA. And so the actual suit will be white for that reason. But he is wearing a prototype of our boots that you can barely see because it's being covered by that micrometeoroid garment. But I do have some more detailed pictures of the boots as well. And then I want to talk about Starliner. I'm sure those of you who are following the news saw Sonny and Butch get stuck on the ISS. And then the Starliner craft had to return empty, basically failing that crewed flight test. And then it recently came out in February that according to NASA, the issues that they had with the capsule were classified as a Class A mishap. It's the first Class A mishap since the Columbia disaster in 2002, which killed all the astronauts on board. So it's a big deal. I'm going to try to keep this as politically correct as I can, but I'm really disappointed with what happened with Boeing because we worked so hard on these suits. These are actually, to our knowledge, the lightest suits that have ever gone to space. So these blue suits, because we were able to replace the helmet with a hood and all these other weight reductions that we did, this suit only weighs 15 pounds, which is incredible. This suit right here weighs like 30, just for comparison. And they're both IVA suits that are designed for, either flying a high altitude plane or low Earth orbit. So yeah, we worked really hard on those suits. So it kind of stunk to be attached to the pork press that mission got. But I just want to state that none of it was our fault. And then astronauts Sonny and Butch really love the suits. One of our engineers in Houston is friends with Sonny Williams, and they text each other regularly. And she just so after being in space for 8 months, she just ran the Boston Marathon. So just comes right back, just runs the marathon, and she's now going to, I saw on LinkedIn, she's publicly announced she's going to be a consultant for VAST, which is another private space company. So a lot of astronauts, when they retire, they'll often be consultants for different private space companies or test pilots. So here's some good pictures of I think this is Chris Ferguson. He didn't end up flying on the mission, but I just thought it was a really cool looking picture. And then this is Sunita Sonny Williams wearing our Boeing suit that we're so proud of. And I just love that it's blue. How often did you see a blue spacesuit? So yeah, it's just a little information, stuff I've already said. Single volume, continuous flow, open loop, air cooled. And the emphasis on this was just how light it was. And then it also had a lot of good mobility in the elbows as well. It was really cool watching them pressurize while wearing them because they could move around so easily, which is so rare for a spacesuit. So this is Barry Butch Wilmore on the right, Sonny Williams in the middle. They were the two that actually went on the mission and ended up being put to work by NASA on the ISS for about 8 months. And then over here is Mike Fink. He was one of the backup crew members who didn't end up flying. He's probably thankful for that. But he was in the news recently. He had a medical incident on the ISS a couple months ago. And he's been pretty public about it. And it's really bizarre. The flight doctors cleared him of a stroke or anything like that. But he said for 20 minutes he couldn't talk. And they still don't know why. And but that was why they had to bring him down for an emergency. It's just really bizarre. I guess you never know what microgravity will do to you, or if it even was an effect of that. But yeah, it was just really interesting, and obviously we're just glad that Mike's okay. But yeah, it's been cool that he's been public about it, just so people can learn about what he experienced up there. And then this is this is our Orion suit. This is probably one of the early, not super early, one of the early prototypes. And then this is actually an EMU suit that NASA was working on. So basically NASA did all this research for a next generation EVA suit that they called the XEVA, XEMU. And we actually worked on various components of it. And then basically they took those lessons learned and they're giving them to Axiom in the development of the next generation lunar suit. So it's like this partnership between all of our companies and NASA. And then this is obviously the suit that's on everyone's mind right now, the Orion suit that just successfully slingshot around the moon and back. That's the farthest that human beings have ever traveled from Earth, approximately 250,000 miles. So this is a closed loop, continuous flow, liquid cooled suit. So they're wearing that liquid cooled ventilation garment, and that's regulated by the ECLS system, which is that environmental control system inside the capsule. It also has touchscreen compatible gloves, non-conformal helmet. So again, the helmet doesn't stick to their face or head in any way. So if they turn their head, the helmet doesn't turn with it. Improved communication system, new state-of-the-art helmet. The reason why I say that, so helmets have historically only had one size, and they were based off the anthropometric dimensions of men in particular. But now that we have women, going into the moon, we wanted to design a helmet that was designed for, a more slender frame, narrower shoulders. Because if you think of the shoulder, the distance from your scapulochromium to your neck, it's like a lever, right? If you push down, it's putting more strain on your neck. So if you have this big helmet with this big neck ring, and you have someone who's narrow, that lever arm, that weight of that helmet is further out on their shoulders, causing strain on their neck. This was a big issue with the ALSS suit when we had female astronauts. They were reporting neck discomfort because of this. So we designed the first small helmet to keep women in mind, and so that it's not putting that added strain on their neck. Now, of course, Christina Cook, who was on the Artemis 2 mission, she was the first one to wear the small helmet. And her feedback was, I told you I don't like the small helmet. I want the regular one. I think she has more broader shoulders like me, so I think that was why she preferred the larger helmet. But I just thought that was funny. We make this helmet with her in mind, and she didn't even like it. It's like, hopefully the next person appreciates it. So yeah, this is talking about how we've tried to take more considerations to adapting these suits to the female body instead of only designing around men in particular, as has been done historically. So this is a picture of astronaut Zena Cardman in one of our extra small ox suits. So this is also the extra small features that we have, including the gloves, are more tailored to women's measurements as well. And then here's a picture. This is my boss again here. I actually don't know who this person is, but yeah, this is my boss. He's the director of our department. And this is a comparison of the size difference between the helmet. So the small is still 95% the size of the original standard helmet. So it's not that much smaller, and it's still created all these design nightmares because it's in engineering. It's not always. It's typically not easy to just shrink something or to make it bigger. It usually comes with all these complications that you didn't think of, and that definitely happened with this smaller helmet. So yeah, this is the XCMU suit that we worked on with NASA, particularly on the boots. So this is a closed loop continuous flow liquid cooled suit. This had an emphasis on pressurized mobility to enable planetary exploration. It can operate at 8.2 or 4.3 psi differential. You all know what that is now. And this is a cool shot of some partial gravity testing in NASA's NBL, the Neutral Buoyancy Lab. So NASA will test all of our suits and our equipment in their giant swimming pool that they have. And this is just showing off just some of the mobility. So again, you could never do this in the old Apollo suits or in the EMU suits, but it's going to be critical now for these new Artemis missions. This is one of the phase 2 prototypes of the lunar boot that we've been working on. I'm particularly proud about this one because I worked on this complicated lacing system here. It works, I don't know if people are familiar with the BOA dials. It's basically popular on a lot of ski boots and hiking boots and snowboarding boots. It's just a dial that you can twist and it'll tighten the boot. So we use that as inspiration for this design here. And trying to figure out how to do that lacing so it tightens evenly was a nightmare. And then also it had to have removable dust protection. So on the old Apollo boots, the fabric that surrounded the blue boot was basically stitched directly to the silicone boot, which is pretty crazy because putting holes in silicone is usually not a good idea. It's not very tear resistant, but it had like a fabric reinforcement in it. So we were trying to work on what we were calling the Ziploc bag. So it was this complicated seal that I had to mold that could then integrate. So you'd have the other side of the Ziploc bag on this fabric portion that would basically grip into it. And you have this rubber gasket basically going around the boot that would allow you to remove the micrometeoroid garment, or what we call now the EPG, the environmental protection garment. But it would also be able to protect from dust getting in there. And we end up scrapping all of this. So all that stuff I worked on is now gone. And that is just the nature of the industry. There's so many things that you'll work on that will never actually fly to space. So I was extremely grateful that the gloves that I worked on for Artemis actually flew, because that's pretty rare for an engineer that's only been at it for 5-6 years. So yeah, the Axiom suit was unveiled back in 2023. I'm gonna have to update this slide because I think we got some newer photos we can share. But yeah, this is just one of the older prototypes of the boots that and we actually. So NASA is actually still experimenting with this boot to this day, and we actually wrote a white paper on it as well, based on the lessons that we learned. And that's it. I apologize if that was really long, but I just wanted to make sure to give you all as much as possible. And if you have any questions, let me know. When we are working on these suits, or when they're working on spacecraft and they have to, look up what temperature this material can withstand, NASA actually has a system called MapThis. It's like a database that you have to ask permission every time you use it, but they'll usually give it to you. Colleges can use it, we use it, and it's basically this material database that will just give you like as much information as you could ever want to know about each material. Now, it's not perfect. There are issues and gaps with the materials in MapThis, and we've run into that with stuff we've been working on, specifically with cryogenic stuff regarding rubbers. So we've actually had to do our own and outsource our own cryogenic research on some of these materials because MapThis doesn't have that information. So that's what Boeing should have done. If they didn't have that information, then they should have performed that testing to confirm that. So again, trying to stay politically correct. Don't want to dog Boeing too much since they are still our customers. So. In the back.
I'm wondering if you could comment on the quality of the Russian spacesuits that are used on the Soyuz and also on the space station.
That's an awesome question. So I do not know too much about the one they were on the space station, but I do have some decent knowledge on the suit that they wear in the capsule. So one thing that we've talked about, so our suits have zippers. So you climb into the rear of the suit, and then you have a zipper that goes top to bottom, and one of those zippers actually seals the air in the suit. So the Russians, in their suit, they have what we call bread bag, and it's basically this. It's either urethane or neoprene or maybe both. This rubber bladder that they get in, and they like bunch up the material in the front, that rubber bladder, and then they like crimp it, and then they tie like a knot around it. I've heard astronauts, like American astronauts, having horrified reactions to this. They're like, wait, you just tie a knot on it? And they're like, yeah, you better make sure you do it correctly. So, and then our Boeing suit, which has the soft hood, one of the inspirations was I just remember the name, it's the Sokol suit. So the suits that the Russians use is called the Sokol suit. The cool thing about the Sokol suit is actually the way their helmet works. So they don't actually have a hard helmet like this. They have a soft hood like we did on Boeing. Now, our Boeing suit is sealed by a zipper, just like the one on the back. So that seals the air. And the Russians, they have, it's like this like rigid metal plastic clamp that basically, oops.
Clamps around your neck.
All right. Yep, and it just clamps the gas container around the neck. And I think it only clamps like here in the front. I'm not fully sure how it works, but I've seen pictures of it. But those are some of the differences. And like I said, we even took some inspiration from that Sokol hood when we were making the suit. Actually, it wasn't our first rodeo. The G5C suit, which I believe only flew on one Gemini mission, that suit also had a soft hood. But that was like what we were looking at for inspiration. We were like, how can we reduce the weight of these suits? And the helmet's just so heavy. So it's like, if you can do something to eliminate that like the Russians did, it makes a big difference.
In some of your earlier slides and throughout the course of your talk, you mentioned needing to consider the probability of like impacts or micrometeorites in space junk. I guess my question is like, how much could the suit actually protect somebody if that were to happen?
Yeah, that's a great question. If it's like a bolt, you're screwed. It's really only micrometeoroids, which are like just super tiny, but they move so fast, like faster than like a bullet. So basically, they wear that white fabric they wear on the outside of the suit. The stuff they use now is called, or the stuff that they're going to use is called ortho fabric, and it's basically this complex weave of like Teflon, Kevlar, like all these really tough fibrous materials. And it's basically this composite weave. It's super expensive. I think it's about $5,000 for a yard of it. And basically it works just like a bulletproof vest. It's designed to just catch those micrometeoroids so they don't puncture the gas container underneath that it's protecting. But yeah, otherwise, basically they have to kind of like check the weather. So basically, if there's like, some space junk that they might, encounter, or which NASA tracks, or if they're on the moon and there's a chance that there's going to be, some larger micrometeoroid particles or something like that, they'll just try to avoid it basically. Same with radiation. So if there's like a cosmic burst or something like that, they're just going to go for cover because the suit's not enough to protect them from that radiation.
We have a question from Greg Shanos in Zoom call.
Oh, yes. Sorry. Yeah, let's get some of the Zoom call questions.
Yeah, hi. My question is, since atmospheric pressure is 14.7, why are the spacesuits 4 and 8? Shouldn't they be 14.7 equal to atmospheric pressure? Can you explain why they're 4 and 8? I don't quite understand that.
Yeah, that's actually an excellent question. So the question was, if the atmosphere here is pressurized at 14.7, well, how come the suits only have to be pressurized at, say, 4.3? And to answer your question is because on Earth, we're only breathing that 22% of oxygen. So that's 22% at 14.7 psi atmosphere. But in the suits, when they're at just 4.3, they're breathing 100% oxygen. So the way the stoichiometry or the way the chemistry works out, if you think about it, right? 22%. Well, so we'll say it's about, let's just call it 30%. Let's just call it 30% oxygen here on Earth, just to simplify the math. And then instead of 14.7, let's say 15. Let's just say the atmosphere is 15 psi. And we'll say 4.3. We're just going to round that up to 5. How many times does 5 go in 15? 3 times, right? So multiply 30% by 3, or 1/3. Now you're at 100%. So now you have that partial pressure of oxygen. You now have enough oxygen to prevent what we call hypoxia, which is the lack of oxygen to the brain. Does that answer your question?
Yeah, okay, very good. Because 100% oxygen, that changes the whole stoichiometry in chemistry.
Changes the whole stoichiometry, exactly.
Yeah, you're right. Okay, thank you very much. I appreciate it.
You're welcome.
I saw a question over here. Yeah. Well, sort of 2 comments. One, I liked how you said if it's a fault, you're screwed. That was really funny. Also, something I remembered about the Challenger thing was that unironically there was a potential that what Big Bird from Sesame Street, like a person in a suit, would have gone and exploded on the Challenger. That would have been even more terrible for the children. But
I remember watching a video on that. I actually did hear about that. Funny that you mentioned it. And what was crazy about Challenger is they were wearing suits on it. It was actually after, so they wore suits for the prototype space shuttles, and then they like weren't wearing the suits anymore, probably for weight reduction. They were like, the shuttle's safe enough, until it wasn't. And then when Challenger happened in '85, I believe. That was when they were like, okay, David Clark, we need suits again. And that was how the ALSS suit, the orange ALSS suit, came to be. And that's what they wore all the way through the rest of the shuttle program. But then there was another disaster, right? Columbia in 2002. They burned up on re-entry. It was because of those, they had a gap in those heat shielding tiles on the wing that allowed that hot plasma to get in. It basically like taking a welder to something and just like melting it apart. And it basically disintegrated on re-entry, unfortunately killing the crew. Now, after Columbia happened, the reason why I bring this up, there was NASA did this huge investigation. They famously tracked down every piece, including the astronauts and all the different components of the suits and all the different components of the shuttle. And they literally pieced it all together in a big hangar and wrote this really thorough investigation. And that investigation was a basis for a lot of the changes that we made for the Artemis suits. It was from some of those lessons learned. So I don't want to get too graphic, but I was talking about the flail stuff earlier. They didn't have flail restraints in the shuttles, so it's like their limbs could have been flying around, being broken. And then also they're wearing these helmets, and it's like a bobblehead, like the helmet's just bobbling around. So one of the things we added on Artemis to protect the neck, there's actually a spring suspension system. It sounds complicated. It's really just a big bent wire, but it basically provides some support similar to a Hans device, like what they wear in NASCAR, if people are familiar with that. But it's basically a suspension system to try to reduce that bobblehead effect to prevent, the neck from breaking in case there's increased G-forces or vibrations. So that's just an example of some of the things that we've changed on the suit just based on these accidents that have happened. So we always try to learn from these things. Sorry if that got too dark. Oh,
I got one.
Dan.
Yeah, you mentioned on the Orion suits, in the event of depressurization in the cabin, they instantly shoot up to 8 psi.
That's correct.
Do their arms like shoot out? Is that?
Yeah, pretty much. Yeah. It's just like it's not quite as bad as a balloon because we have a restraint layer that tries to mitigate that. But yeah, basically they just and then you're not moving that much. And again, they're not going to stay at 8, right? It's just to get them acclimated, and then they can just turn themselves down. Or I think the capsule can also turn them down to 4.3, where now they have all that mobility again for whatever they need to do.
Given all of the lessons and improvements that are implemented, what is the current potential greatest fault of the current designs that you've seen?
That's a tough question. Let me think. So I guess what I can think of off the top of my head is sometimes we'll spitball, what's the most expensive, most inefficient part on these spacesuits and how could we get rid of it? And the answer is that really complex relief valve I was talking about. The design of this thing hasn't changed since like the 1960s. And it's the most expensive part on the suit. It's probably some eye-watering 6-digit number to make just one of them now. It takes a ton of skill to make them, and they also weigh. Obviously it's not that heavy, but for a spacesuit it's heavy. It's like maybe like 2 pounds or something like that. And so we've tried to think of ways of is there a way we could eliminate the suit controller? And one of the companies that has done it is SpaceX. Now, the reason why SpaceX gets away with doing whatever they want with their suit is because they control the design of the capsule. So if you remember from my slides, I was showing the Boeing suits. We're hostage to whatever Boeing wants because they're the ones designing the capsule. So we have to design around Boeing saying we're going to integrate with this, and you have to do all that. But with SpaceX, because the company's completely vertically integrated, because they can design the suit and the capsule together in conjunction. So they can say, well, we want to get rid of the suit controller. So what they do instead of having a suit controller is they just have high pressure air running into the suit, and the suit just leaks like a sieve. So basically the suit's just leaking like crazy, but they're pumping in air so much that it's negligible. Now, do I think that's the best design? I don't know, but they did it, and then also they were lucky. They were able to 3D print their helmet. I don't know if people are familiar with 3D printing, but they were able to 3D print their helmet. They basically, as soon as they came out with that 3D printed helmet and got approved for flight, NASA immediately came out with all these new standards and requirements that have to be met for 3D printing. And it's just so much that it deterred us from doing it because we wanted to look into making a 3D printed helmet. But then when we read through that new document, that new standard that they came out, we were like, oh my gosh, there's just so much testing that we have to do that it would just, the cost would just be ridiculous to pursue something like that. So it doesn't rule it out. We might do it in the future, but it's just those are some of the things that SpaceX was able to do because of how much control they have with their capsule. And I would say that we would like to do similar stuff with our suits. We just lack that freedom since we don't control the design of the capsule.
Time for maybe one more.
What does a suit cost? Can you give us a number?
Yeah, that's an excellent question, and a really
Generation. What would the next generation one cost? Because I know I heard it cost $70 billion for that trip around the moon. So I must have gotten like at least $1 billion out of it.
If you saw our building, you would know that number is not true. It's hard to put a price on those spacesuits because it's basically all R&D. It's all labor. The materials itself, I don't know, maybe 50,000, something like that. I'm just spitballing, but I can say for this suit, This one I think is roughly $300,000, but it's because it's our mass produced suit for the Air Force, so that one we can more easily put a number on. But for like the Artemis suits, if I had to say, I would say probably about $2.5 million for those suits. And then again, most of that is just the development cost. But yeah, I would say if we were to like put a price on that suit, it would be like, it'd be 2.5 million per suit. But yeah, that billion number that's been getting thrown around, so that's more in reference to the lunar suit that NASA was working on, the XEMU. So they were getting kind of, interrogated by the Office of the Inspector General in Congress because NASA was doing all this experimentation, and then basically they were like, oh, well, you guys, it was like, oh, so you did all this stuff, but you didn't have a flight ready suit. However, NASA never said they were going to come up with a flight ready suit. They were just going to try to work on different things, like different experiments to try to develop knowledge to make a new suit and then pass that knowledge on to the private companies. So that's where that more billion-dollar figure comes from. And the response that I give to that is we haven't built new EVA suits since the 60s and 70s. Those EMU suits that they're using on the ISS, that technology is all dated back to like the 70s and 80s. There's been so much new materials, so much new technology. So if we want to take advantage of all that, it's going to cost some money to experiment with all those new materials, and we're doing that on our boots as well. So the low Earth orbit boots that we're working on for the next generation EMU suit is all new materials. One of the materials is a plastic that's only existed since like the 90s, I would say. And again, it's just all the work that goes into like how safe is that material? Does it meet all the requirements? And then you get into the issues of manufacturing it, and then you might use it in the pool, and then you find a new issue with it, and that's just where all the spending the money comes from. It's just all the labor hours, all the experimentation, all the R&D. But that's a really good question.
That was a great talk. Thank you.
Thank you so much.